Let's talk about the height of a projectile. So this works near the surface of the Earth with this constant in there for the acceleration of gravity. The height of an object that is projected into the air at v sub 0, or v naught sometimes we say, feet per second, from an initial height of h naught feet is given by h, the height, equals negative 16 t squared plus v naught t plus h naught, where h is the height in feet and t is the time after the initial launch in seconds. The equation does not account for air resistance. So if you think about it, how would you account for the total height of something that's being tossed in the air? Well, you might start with the initial height, where did it begin? Then you'd take the velocity that it was launched, so if that's feet per second, you'd multiply it times the number of seconds, and that makes sense. That would be the effect that the initial velocity would have on it. Finally, you'd have to account for gravity. Now this accounts for gravity. The units for gravity are feet per second squared, and so you'd need to multiply that times time squared, times second squared, to get the effect on the height in feet. Notice it's negative because the gravitational pull would pull you downward. Okay, so let's look at this problem. If a rock is dropped from the Golden Gate Bridge and the roadway is 220 feet above the water, when will it hit the water? And give your answer to the nearest tenth of a second. Okay, so when will it hit the water? That's asking when will the height be 0? So if we're going to put this down, the constant is always negative 16. Well, what's dropped mean? That means that it's not thrown. That means that the initial velocity is 0, and of course it's starting at the roadway of the Golden Gate Bridge. So I have this equation. Now I'm going to move this piece to the other side. I'm going to add 16t squared. Since the variable only occurs once, I'm going to try to isolate the variable. I'll divide by 16. I'll take the square root. In general, this equation could be solved by positive or negative the square root of 220 over 16, but recognize because this is time past, I'll just take the positive value. Now what I'm going to do is I'm going to approximate that to the nearest tenth. I have a calculator here, and so what I'll do is I'll take the square root of 220 divided by 16. And so I'm going to write 3.7 seconds. Now, if a rock is tossed upward at a velocity of 10 feet per second from the Golden Gate Bridge, so that it lands in the water, no fair landing back on the bridge, when will it hit the water? Again, answer to the nearest tenth of a second. So, again, it's going to hit the water. Gravity stays the same. Now we have a velocity of 10 feet per second. Now notice the variable doesn't show up just once, so really isolating the variable is much more difficult. We could try to factor it. You could also try the method of completing the squares. If you don't see how to factor it initially, I will often use the quadratic formula though. T is equal to negative b, so negative 10, plus or minus the square root of the linear coefficient squared, b squared minus 4ac. A is the quadratic coefficient, c is the constant term, all over, notice that division line goes all the way, 2 times the coefficient of the quadratic term. Okay, so that's what I have. I'm going to bring back in my calculator here. parentheses are really important here. I have to divide this entire piece, so I'm going to put parentheses -10 plus the square root. Notice they open a parentheses telling me that my square root is beginning. 10 squared minus 4 times -16 times 220. That parenthesis ends my square root. That ends the numerator, divided by. Now, if I don't put in parentheses here, it won't know that I'm supposed to divide by the entire term here. So parentheses are really important, particularly indicating the numerator and denominator. So, that doesn't look so good. -3.4. Okay. Well, now notice you can press second and entry on a TI 83 or 84. On a TI 30, you need to press the up arrow to get back to the initial code. And notice we had a plus or minus here, so I'm going to change this to a minus. That's the other solution. Now I get a positive solution. So one solution didn't make sense as far as the time. The other solution did. This is 4.0. So this happens at approximately 4.0 seconds. Well, that's sort of reasonable. Okay, throwing it up faster, throwing it up in the air, made it hit the ground later. Okay, last but not least, if a rock is thrown upward at a velocity of 40 feet per second from the Golden Gate Bridge, when will the rock be 230 feet above the water? Again, answered in the nearest tenth of a second. So now I have my initial velocity slightly higher, still off the Golden Gate Bridge, but notice I'm not setting it equal to 0 here. I'm setting it equal to 230. How do you solve this? Well, you subtract 230 from both sides. Now you can use the quadratic formula again, or you can factor. Okay, so we have here t equals -40 plus or minus the square root of 40 squared minus 4 times -16 times -10 all over 2 times -16. So, sort of a similar procedure here. We're going to have -40 plus the square root of 40 squared minus 4 times -16 times -10 divided by 2 times -16. Okay, so answer, well, notice this is a very small number. So after 3/10 of a second, it will be 10 feet higher than the base of the bridge. But we can also have an answer as follows. I'll go back to that. Make that a negative. Also, notice that it goes up and it comes back down after 2.2 seconds to a height only 10 feet higher than the top of the bridge. There you have it.